In this first video for Chapter 9, we're going to define what an infinite series is and then see how we determine whether these infinite series have sums that are finite or infinite, which we call converging or diverging. So first let's define an infinite series using this notation. So an infinite series would be a sum, using the sigma notation, from n equals 1 to infinity of the terms a sub n. And if we write those terms out, it would be a1 plus a2 plus a3 plus, and it just continues. Well, it turns out that sometimes when you add an infinite number of terms together, you get a finite result. You can even find the sum of these results in some cases. And we want to, in this chapter, look at when or how to determine whether that sum is finite or infinite using a variety of what are called convergence tests. We also want to look at some very important specific infinite series that define functions that you have a lot of familiarity with, such as cosine, sine, tangent, and logarithm. So let's put some pictures up to help us understand the first convergence test for infinite series, called the integral test. So let's suppose that we have a function f of x as represented here, and that we are finding rectangles at these x values. So here's 1, and this height right here is f of 1, and here is the x value 2, and this is the height f of 2, etc. So we can see from this graph that if we take the function values, or the height, the rectangles of height f of 2, and all of these rectangles have width 1, so let's indicate that the width is 1 just in this first case. So f of 2 plus f of 3 plus dot dot dot, all of those is, that's these lower rectangles here, right? The area of those lower rectangles, that is less than or equal to the integral under f of x between 1 and infinity, and that in turn is less than or equal to the area of all of these rectangles that are above the curve, and those rectangles have heights f of 1 plus f of 2 plus dot dot dot. So the difference between these two sums involving the function f, this sum right here and this sum right here, is that this one starts at f of 2 and this one starts at f of 1. So let's continue on the next blackboard to write this in a different way. So we have what we had from the previous blackboard rewritten, and now let's give a different name to each of these function values. So instead of calling this f of 2, let's call it a sub 2, a sub 3, a sub 4, and that of course would still be less than or equal to the integral of f of x dx on 0 infinity. And then we're going to continue with this naming convention, a1 plus a2 plus a3 plus dot dot dot. So this notation that we are using here with the a notation, this is the infinite series notation. And this notation up here is the function notation. So what's the difference between them? there is a little bit of a difference. We're not just renaming things. Let's go back to our picture over here and use this graph to explain what's going on here. So when we refer to these f values, f of 1, f of 2, f of 3, etc., they are the areas of these rectangles. Right? So there's f of 1 times 1, there's f of 2 times 2, etc. And when we refer to the a values, so what's the difference between a1 and f of 2 times 1? Well, a1 would just be this. a1 is just this height right here. And this height right here is a2. This height right here is a3. So let's note those. Here's a1. Here's a2. Here's a3, etc. But it turns out that they are exactly the same, right? Because these heights and these rectangle areas, and I've rewritten it slightly to put a 1 in front to represent the width of each one of these. So these all are rectangle areas, and these here are all just the rectangle heights. But they're the same because the widths are just 1. So that gives us this new string of inequalities. So let's just write this sum right here a little bit differently. This should have a plus dot 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 on it. Summation n equals 2 to infinity of a sub n is less than or equal to 1 to infinity f of x, the area under the curve, is less than or equal to the upper heights, which is the sum from n equals 1 to infinity of a sub n. So this, if we box this in right here, this this is what we call the integral test for infinite series. And why is it a test? It says that we can, if we have an integral that converges, then this series converges because it's less than or equal to the integral, whereas if we have an integral that diverges, that has infinite area, then the series is going to diverge because it is greater than the integral. So it can be used either to determine convergence or divergence. So let's see how we do that in a couple of examples. So this series, infinite series right here, n equals 1 to infinity of 1 over n, which is 1 plus a half plus a third, etc., is called the harmonic series. It actually has to do with harmonics in acoustics. And we can determine that this series, or whether this series converges or diverges, by converting it into an integral that we can test whether it converges or diverges. So how do we do that? We turn the sum sign to an integral sign. The limits of integration are just the beginning and ending values of the series, 1 and infinity, and then we just change the variable, the series n, to x and integrate dx. So this is a series that we already know from chapter 8 discussions. Diverges. It's actually what the limit as m goes to infinity of ln x between 1 and m, which we have already seen is infinite. And so using this form of the comparison test, So we know that this integral diverges, and therefore our series diverges. So that's an easy way to show that the harmonic series diverges. It has an infinite sum. By the way, this series does not by any means diverge quickly. Let's take a look at it for a second here. So this series 1 over n, the harmonic series, diverges very slowly. With 100,000 terms, its sum is about 12. 10 times as many terms, up to 1,000,000 terms, 14. 10 million, we're only adding 2. So each time we add 10 times as many terms, we're only adding about 2 to the sum. And each time we're doing this, we're adding a huge number more terms, right? We're adding 900,000 more terms going from here to here. And going from here to here, we're adding 9 million more terms. Here we're adding 90 million more terms. And from here to here, we're adding 900 million more terms. So that gives you a good idea how slowly it diverges. We can also use the integral test to look at the infinite series n equals 1 to infinity of 1 over n squared. If we convert that to an integral, it is its corresponding integral is 1 to infinity of 1 over x squared dx. Remember, this integral and series are not exactly the same. There's this set of inequalities that defines it, but they are close enough. So here, let's take a look at this convergence version. We know that the p series 1 to infinity dx over x to the p, we proved in the last chapter that converges to 1 over 1 minus p, and so that means that this sum is 1 over, I'm sorry, not 1 over 1 minus p, 1 over p minus 1, and so the sum of, or the sum of the integral 1 over x squared would be 1 over 2 minus 1, or 1. And remember that this is greater than or equal to the sum from n equals 2 to infinity of the series. So the series of all terms except the first term is bounded above by 1, and so that means that we have that the series itself with all of its terms in n equals 1 to infinity of 1 over n squared is less than or equal to its first term, which is 1, right, plus the sum that we got. So it's bounded above by 2. And if you look in the textbook on page 194, you see that if we sum up 10,000 terms of it, it's 1.07, and that a better upper bound for it is not 2, a little more closer upper bound for it is approximately excuse me, that's not right. The upper bound, or the 10,000 terms of this is not in the textbook, but I just did it on computer software and got that it is approximately this. So we use the integral test for convergence. It gives us the convergence of, when the integral converges, it tells us the series converges starting at n equals 2, and then we have to add in the first term of the series to get an estimate of an upper bound. So let's apply the integral test once more to another series. So we find the corresponding integral, which is 1 to infinity of dx over x squared plus 1. That is the tangent inverse integral. So it's tan inverse of x between 1 and infinity. So we have the graph of y equals tan inverse of x over here, or at least a part of it when x is positive, and so tan inverse of infinity minus tan inverse of 1. You can see from the graph tan inverse of infinity is pi over 2, and tan inverse of 1 is pi over 4, and so that integral converges to pi over 4, and therefore the infinite series is less than or equal to pi over 4 plus its first term. Its first term is going to be 1 over 1 squared plus 1, which is a half. And that, as shown in your book on page 194, gives an upper bound of about 1.285 for this series. So that's going to conclude this video on the first section of Chapter 9 on infinite series and the integral test.